Okay, so we're on our fourth and final slide of examples of derivatives of exponential functions of base e. And in this question, we're asked to show that the normal probability density function f of x equals 1 over square root 2 pi times e to the negative x squared over 2 has inflection points when x equals plus or minus 1. So the normal probability density function is given to you, as is its graph. And what we're trying to do in this particular problem is show that the inflection points occur at plus or minus 1. So let's just take a moment to review what inflection points are and how we might go about finding them. So they're telling us that the inflection points are at negative 1, which would be about here, and positive 1, which would be about here. So we referred to these many months ago as IPs, inflection points. We have an inflection point over here, and we have an inflection point over here. And an inflection point is a point in which the concavity changes. So our graph, originally, reading it from left to right, looks like it's concave up. And then here, it's concave down, C, C, D, concave down. And then it changes again to concave up. So the fact that the points of inflection are at plus or minus 1, it seems to be reasonable because it looks like that's where the concavity changes if I were to project up like this. As a reminder, what facet of derivatives do we need to consider when looking at concavity and inflection points? Well, if you guessed the second derivative, then you're correct. So we're going to first find the first derivative, and then we're going to go on to find the second derivative. So let's keep in mind that 1 over the square root of 2 pi is just a constant. So while it looks really scary, we're just going to set that off to the side, and then we'll just tack it back on at the end. So let's start with the first derivative. I'm going to start by just writing that constant. Now, when you're taking the derivative of e to some power, you just rewrite the whole problem. And you'll notice I chose to write it in a little bit more, to me, of a way that's easier to work with than the way they gave it to us. And now that I've rewritten the problem, I have to multiply by the derivative of the exponent itself. So if we think of u as 1/2 or negative 1/2 x squared, its derivative is simply going to be negative x. So there's the first derivative. And I'm not even going to clean it up. I'm going to leave it like this because I'm just going to go on to the second derivative anyway. But what I want to do now is delineate what I'm going to consider the first function and the second function, because I'm going to need to use the product rule. So I'm going to call this the first function, and I'm going to call this the second function. And I'm going to make my little organizational chart off to the side. So the first function is e to the negative 1/2 x squared, and its derivative is going to be a restatement of that exact problem times the derivative of the exponent. We just did this, so that's going to be times negative x. And the second function is negative x, and its derivative is negative 1. So now I'm going to find that second derivative by implementing the product rule and not forgetting that constant that's out in front. F double prime of x is going to be equal to that constant. And now I'm going to get ready for the product rule, which is going to be the first times the derivative of the second plus the second function, which is really minus x, because the second function is minus x, times the derivative of the first. Now the derivative of the first also has a minus in it, so that's going to make that a plus. And it introduces another x, so I'm going to say x squared and then e to the negative 1/2 x squared. Definitely a lot going on here, so if you're feeling overwhelmed, you're probably not alone. So I'm going to come down here where I've got a little bit more space, and I notice that this e to the negative 1/2 x squared is present twice inside of these grouping symbols, so I'm going to factor that out. So I've got this constant out in front, 1 over the square root of 2 pi. I'm going to take out e to the negative 1/2 x squared. And when I take that out, I'm left with x squared at the end, but I'm going to write it in the front. And I'm left with negative 1, which I'll write here. So just to be very clear, this x squared went to the front, and this negative 1 went to the back. and then these two elements I factored out, and that's why they are not in the parentheses anymore. Now to find inflection points, we take that second derivative and we set it equal to 0. So if we do that, if I actually set it equal to 0, this constant in the front is not going to have any impact whatsoever. Just think about dividing both sides by that constant. It's going to go away. Now let's move to this over here. If I set this equal to 0, e to the negative 1/2 x squared, there's not going to be any such x which will make this true. So there will be no x for which this will equal 0. So this is not going to contribute anything. And that, of course, leaves us with this. And if we take x squared minus 1 and set it equal to 0, we get x squared equals 1, or x equals plus or minus 1. So at this point, I've convinced myself that if there are inflection points, they're going to be at positive 1 and negative 1.